It's great.
Yeah, am I audible?
Yes, you are audible.
Yeah, yes,
Okay.
you. Good to go. Yeah. So you can just do for like full screen, your presentation and full screen mode.
Yeah, and to minimize it.
Yeah. Got it.
Yeah. So we'll start at 5. Okay.
Mm.
Okay, we'll start at 5. I have 5 minutes. Right?
Yeah, you have 5.
Yeah, 5 to 6 minutes. Yeah.
Okay.
Anupma will announce when to start. I request the participants to turn off your video feed.
Okay. Okay, fine. Fine, it's working. Thank you.
Cinca, leo baixo. Olha. Uri. Arti.
I request everyone to kindly mute yourself.
It is mandatory for the participants to turn off their audio and video feed during the lecture. When there is a time to turn it on, Anupma will inform you. Good evening, everyone. Anupma, I think we can start now.
Okay. Good evening, everyone. I thank you for joining us today for the fourth session of IEEE NTC Virtual Talk Series on Advanced Materials. So today we will be focusing on water treatment. So as you all know, water is the vital source of life. But today, water quality is a challenge. And this water quality is getting degraded because of the geogenic and anthropogenic activities. So now, where does nanotechnology play a role in water treatment as well as monitoring? So to discuss more on it, we have our today's speaker, Mr. Deepak Panchal, and he's currently working as research scholar at CSIR NEERI and enrolled at ACSIR. And he's been working at the Department of Wastewater Technology Division. And his research interests are basically focused on nanomaterials for water treatment. So with this brief biography, I welcome Mr. Deepak for your talk. Yeah, over to you, Deepak. Yeah, Deepak, you can unmute yourself.
Yeah, okay. Wait. Yeah, I'm already unmuted. Can you?
We are able,
Yeah, yeah,
we are
yes,
able
you're
to hear
audible
you.
now. Yeah, okay.
Yeah. Okay, fine. So today's theme is to be the discussion of the advanced materials for water treatment. So I'm gonna talk about it. The first we should know what is the problem. So as Anupama introduced, the problem is with the water, which is a basis of life, and the primary uh, barriers we have right now in our country is the wastewater treatment plants, where we have different type of plants like the sewage and the municipal and the common effluent treatment plants, and they have different type of steps they are trying to reduce the pollutants in the water or the streams or anything else which is coming inside it. So the generation of spreading of these pollutants, also these ATPs plants, when they are not performing efficiently, the discharge or the treated or untreated effluent will get into the drinking or the groundwater facilities, and then we see the contamination. So the how the pollutants can be of three types, like pathogenic and inorganic and organic. Pathogens, we have various microorganisms and the viruses, and the inorganic, heavy metals. Organic as the dyes and the PCBs and CECs and etc. and everything else. So the conventional method right now we have is the wastewater treatment plants. As I've said, we have majorly the three steps: the primary, secondary, and the tertiary. Primary basically related to the physical separation of the pollutants from the water. The secondary deals with the biological processes where you have many bacteria and bacteria and the other consortia of bacteria which reduce the organic load by eating or degrading them. Then the tertiary is the main where we actually separates the micropollutants from the water, but are they actually adequate or not? It is still questionable, because when you go for the monitoring, you will find that there are a lot of still there are a lot of many pollutants in your water. So they in even in the better wastewater treatment plants, the people are using the activated carbon and the sand filtration, which is not even up to the mark. So we need to enhance or to efficient these technologies by application of something which is very good or better than them. So once in a conference, I asked these questions to one of the nanotechnologists. Then he said the application of nanotechnology in wastewater is nano right now. So that question triggered me to that why he's saying that like that, because there are a lot of papers in it. So I goes through it and I found what is a nanoparticles. First, I start with what is a nanoparticle. Very briefly I'll discuss it. The particle which has the size between 1 to 100 nanometers is a nanoparticle. So it can be metallic and non-metallic, or it can be polymer, and their application are majorly based on their surface charge, the surface shape, the surface size, and the tunable surface area and the band gap, which is used for the photocatalysis or the other applications. So actually, what a nanoparticle can do, it can perform scientifically, it can perform the photocatalysis, oxidation and reduction reactions for the degradation of organic compounds on the halogenated organic compounds. It can transform the lower oxidation states to higher, or like the transformation of the oxidation state, so that the pollutant pollutant activity can be minimized. The sorption is the easiest method. The like the adsorption I'm talking about. Adsorption is the best method which has been currently used by everywhere in the water treatment systems. And photocatalysis, where titanium oxide is very famous for producing the ROS, which can degrade the organic compounds and the pathogen. So, what a particle should have to be performed as an adsorption phenomena, the famous are like carbon nanotubes and the other higher oxides nanoparticles. They should have a higher specific surface area. They should be like easily minimized in the environment, or they should not show any chemical toxicity towards the environment. Again, if you go for the membranous structure, which is now the membrane structure is being updated by the application of the polymers or the AG or the TiO2. So they should be first they should have a very high specific area for the membranes, and these particles should not leach out of the membrane also. The photocatalysis are representative nanomaterials like TiO2 or the other heterocatalyst. They should be showing the enough electron hole pair reduce the electron hole pair recombinations, and should be low cost also. For the disinfections, we have nano ag, nano TiO2. For sensing also, the material should have higher lspr, should show the higher lspr activities. uh, this is the just the briefing of potential of nanotechnology. So what are the methods currently we are opting for synthesizing? One is the top down, other is it bottom up. The top down is the reducing the bulk material to up to the nano levels. So we have different type of active different type of methods like ultrasonications, where we have bulk materials. We keep that in a solvent or aqueous form, and we apply the ultrasonication. With that huge energy, the layers get separated into the monolayers. The ball milling, where the various metallic balls applied the shear force on the several several materials so that they can be degraded into, that can be lower down to the nanoscales. But the problem with the ball milling is that there can be the huge contaminations. The laser ablation also, laser ablation, we apply a huge powerful laser beams which vaporize the material into and condense, which vaporize the material first, and then it get condensed in the proper solvent or aqueous form into the nano particles. Again, the laser ablation requires the huge electricity. That is the disadvantage of it. The bottom up approaches are generally followed because of their easiness or the yield. So CVD, which is famous for very pure, like pure substance. If you want to synthesize a very pure substance, you should go for the CVD. Here, the material is kept in a furnace. You can see, here the material is kept in the furnace, and one is the other material can be kept in the other place, or in a ceramic boat. When you apply a high temperature, the one of the one from these substrate get solubilized, sublimized, and deposited on the others. So you can also go for the double split, like if like sulfur has a lower boiling points, and so if you keep it keep it in a separate zone where the temperature can be controlled, you could find a different type of materials or the films over the substrate. But the problem with it, you will find a very small yield into CVD. The hydrothermal is the best method in my view, because you can get the yield high, and where a small instrument is there, which is called the Teflon lined autoclave steel, which is jacketed by the steel, and you kept your all the reactants in it, and you keep that reaction sample in the oven for a time, and you get the very purified and highly crystalline nanostructures. The thermal decompositions, where you have your reactants and your capping agent and surfactants, and you boil it for some times, and then the nucleation started, and with the growth you will get the nanoparticles. These are the methods, and after synthesizing, you need to know whether you have synthesized your material or not. So you should actually see whether your materials has synthesized. The first should be the XRD, whether your material is actually what have you want to be. So you can go for XRD, then you can go for IRs, you can go for XPS also for the further confirmation of the oxidation states. And for the size, you can go for the microscopic techniques, the SEM and TEM. And the other chemical characterization, you can go for the zeta potential for knowing the charge on your surface of material, then surface area. So these type of application will give you the surface and the morphological information, and the chemical composition, the functional group, and the texture. So coming to the application of these nanomaterials, so as I was telling, the carbon is being used. So in wastewater treatment plants, if you visit some wastewater treatment plants, you will find activated carbons fitted into a tubular surface, a tubular area where the water is being applied into it with the pressure, and you will find a clean water. So but that is not, if you go within the literature, you will find the CNT are the better materials than the activated carbons, because they have a huge surface active sites. One is the intratubular, the second is the interstitial surface, the fourth is the ingrooves, the third is the ingrooves, and the fourth is the surface area, which is the periphery of the materials. But you will find the distance, this this pore size is very small, like 0.3 nanometers, so no pollutant can be absorbed in this area. So majorly the active sites is the outer surface. So this is an example of removing the methylene blue by the various mechanism given by the CNTs. So because of the various functionalization or the various functional groups present on the surface of CNTs, the dye can be removed by the electrostatic interaction or the pi stacking. So again, after the CNT, the graphene oxides came into the context of the people because the huge surface area and the higher functionalization. This is the graphene where it is uh, changed into the sulfamic acid, and then you will get some other functional group over it, and that paper is showing the multifunctional activity of the graphene oxides, where you can remove the heavy metals and the methylene blue at the same time. So after getting the graphene oxide into the world, people have started looking for increasing their functional group. So they have started applying different type of material to it. This is a a very good example of functionalization of the graphene oxides. So they use the Dopamine is a self-polymerizing compound. So say that simply put the graphene and the polydopamine together, and you find there is a small cube present inside the this vessel. And this vessel is was when characterized was found to be highly porous. And you don't need to go for any hydrothermal route and anything. You just need to put these two candidates together, and you will find such type of material. And when you incubate this material with the higher pollutants like benzene or heavy metals or the dyes, the the huge adsorption capacity can be achieved. So these were the some advancement in the nanotechnology, which enabled you from jumping from carbon nanotubes to the graphene to the this PDA influenced hydrogel. And uh, after this discussion, then people started looking for the metal oxide because of their tunable surfaces. So this is the example where the iron oxides, where the ferric oxyhydroxides holosphere were formed. So for synthesis of such type of structure, you always need a surfactants. But this method was needing no any templates, no surfactants. They just just changing the concentration of glycerol and putting it to the hydrothermal unit, and they by changing the temperature and just by the quantity of the glycerol, they are able to get such type of hairy structures. And then this structure was analyzed. It was found to be 96.9 meters square per gram. Such a huge surface area enabled it to absorb the Congo red and the arsenic and the lead at the same time. So this is also one good example for getting the multifunctional activities from from a template free synthetic protocols. And after that, people have started looking for how to again improve the active sites over it. So they started encapsulating these uh, nanomaterials in some surfaces. Like this is an example where the uh, carbon surface was chosen with the porous structures, but you cannot just simply add your nanoparticles into it. So when you simply go for it, you won't find such a surface area. So for what he did, he applied the um, he performed the experiment in the ammonical environment, where the subsequent pyrolysis was done. And what he found such type of materials where there is a surface of CNT, where the surface of carbon mesoporous membrane is also, which is able for the active sites, where there your material, where there your uh, iron particles, which is also encapsulated into it. And after this, he was able to remove arsenic 4, arsenic 3, and arsenic 5 together. And uh, because of the presence of the iron, he was able to just simply able to remove your material for regeneration. He applied the external magnetic field and able to regenerate his material. This is one more advancement in the layered structure. After graphene, the molybdenum sulfide was very famous for its surface area and the functionalization over the surface. You find this is structure of MOS2, which has the interlayer space of 0.62 and a free space of zero point 0.3 nanometers. So these surface have a very low covalent or low van der Waals attraction in between. So when you go for the ultrasonication, these layer can be separated from each other, and then you get a monolayers. And these monolayers have a huge surface area for removal of any type of pollutants which is cationic. So because the surface is functionalized with the sulfur atoms, so they act as a soft base, where the metal contaminant can be removed. So this is the mechanism. This is where the sulfur layer is negatively charged and able to replace the hydrogen atom from it, and the metal can be adsorbed directly over the surface over it. So there can be two mechanism. One is the outer layer in electrostatic attraction. One is the metal sulfur complexation. So after knowing about the molybdenum sulfates, people again started reading about it and studying about the phenomena, how to synthesize it, and how to okay. Hello, Anupama.
Hello.
You can stop sharing your screen and again reshare. Yeah.
I can stop.
Sharing,
Oh,
then again reshare. That would help this gray window to go.
okay. Is this fine?
Yeah, fine. Yeah,
Yeah.
good. You can go.
So
Okay.
they have started studying this material. So they knew the van der Waals force are very weak. So they try to separate it from each other. The surface area can be increased, or in other sense, the unaccessible sulfide which is there inside the layers can be accessible for the pollutants. So by just increasing the amount of your reactants, which is thiourea, they increase the thiourea higher ratio and able to create such defects in the layer also. So you see in the previous slide, this is a defectless layer, and you see in this side after increasing the thiourea, you see some defects in the air or they defect in the layer, and they also verified it with the TEM images, and the lamellar structure is broken up. You can see they have highlighted by the arrows. So by degrading such orientation of a surface, you get the surface is very exposed to the pollutants. Now the sulfur is very exposed and accessible to the pollutants. So just by playing with the reactants molar ratio, they are able to generate the defects in the orientation of the nanostructure. They are also able to increase the lamellar interlayer space. And also they verified it by the XRD also that the shift, the peak was here before. I haven't shown you the picture. The peak was here at like 14 something, and there the D spacing was 0.63. Now the peak is shifted around 10, and the basal plane, which is found to be 002, has the D spacing of 0.9 nanometer or 9.4 angstroms. So this increase the lamellar surface, lamellar spacing, and also creates the defects where the uh, binding capacities of the material was very high. So they use this application for the mercury removal, and you can see the difference in the adsorption amount, which was around 50 has been raised to 2500. That is so excellent result which is shown by them. And these all actions were related to it. Now we come to the photocatalysis, where the can play again a very important role in the water treatment facilities or water treatment applications. So generally photocatalysis is applied by any material which show the good separation between the electron and the hole. When the TiO2 is the most widely or most exploited semiconductor in the wastewater treatment also. You see there is a difference in the valence band and the conduction band of the TiO2 when the photon energy equals to more than the band gap of the TiO2 falls over it. So the electrons will jump to the conduction band, and after reacting with the oxygen in the environment, they form the superoxide ions, where superoxide ROS where the superoxide can interact with your organic compounds and degrade it into the lower compounds. Also, the holes present in the valence band of the TiO2 can react with the water molecule and can produce the hydroxyl radicals, which is again non-selective radicals, which can degrade any compound or any higher organic compound or the your bacterial species. Also, if you are able to control the facets, like one of the scientists was showing, the 001 phase of TiO2 is more efficient for the hydroxyl radicals, and during the crystal growth, this 001 changed to 1, I guess I haven't named it. The phase change and the for producing the hydroxyl radical also change. So if you are able to cut phase, then keep this application of TiO2 for producing the hydroxyl radicals. How they did it? They usually they just use the capping agent, which is fluoride, and prevent the phase of it, so that the production of hydroxyl capacity can be maintained. Another application is, where TiO2 requires the UV light. If you dope them with the noble metals, you can directly into the visible region, because the electron can jump directly to the surface of uh, available, which is uh, silver, or if you apply the silver or gold, the electron come to over it, and where they get the separation can be maintained, and that and can be the recombination can be delayed, where the uh, other arrows can be formed. So how you jump to the CB and then jump to the conduction band of where the ions formed, superoxide radicals formed, and which able to degrade the methylene blue, which is again organic dye, and you found the lower components, where again the important role. Another application, another mechanism can be also given, where people have shown this. The electron from the CB of conducting materials jumps to the lower CB, or because it is situated at the lower position, the electron jumps to the CB of TiO2, and the holes present in the VB of the TiO2 jump to the VB of the conducting materials, where the separation is maintained. Again, you can get the ROS, which is used for the organic pollutant degradation. So this application was very nicely adapted by this paper, which was being published in Langmuir, where what they did is synthesize the layer double hydroxide, which is a positively charged layer sheet. uh, this is more similar. This not more or similar, but you can, amust is also layered sheet. This is also a layered sheet, but this is positively charged. They have inter. They, this is a layer structure, and find various anion species here in between the layers. So what they did, they delaminate it, and just by simply delaminate, they get recombined again with the electrostatic attraction. So what they did, they reduced, they exchange the carbonate ion with the nitrate first, because carbonate has the high hydrogen bonding attraction between each other. So the layers get again reconstitute. So they interchange with the nitrate ions, and intercalate the TiO2 by putting the TiO2 in the formamide solvents. So after putting the TiO2 and the LDS together, they get this structure of LDIH and TiO2. So now they have one adsorption surface, which is LDH, and now one photocatalyst, which can act which can play the photo degradation of organic compound when UV light will fall. So they use this material for photocatalysis and adsorption together. But from these application together, you won't find such good capacity to remove the pollutants. Why? Because they extend it. Because when you go for adsorption, your pollutant will occupy the space of or you cover the surface of TiO2, and which is not able to extract the, or where the light cannot be fall upon this TiO2 surface, and the electron and hole pair will not generate. So they suggest to separate the adsorption and photocatalytic process. So what they did, they take the contaminated water, they first go for the adsorptions, and then after a time they started the photocatalytic degradation, and so the remaining pollutants can be degraded by the photocatalytic actions. Another application, they took it from it for the regeneration of the materials. They use this material for they use this material for adsorption of the heavy methyl orange and the 2D4, which is a pesticide. And after a time, they apply the UV light. You can see here, which is a slow process. But they, when the light falls over TiO2, their hydroxyl radical produced, and these hydroxyl radicals can again photo degrade this pollutants, which is intercalated between or on the surface of the materials. So this is freeing one more site again. Now the sites is again activated and it can absorb another molecule. So this type of application has been exploited with the combination of adsorption and photocatalysis together. Now, now people have started using the 2 3 types of materials together to form the nanocomposites, and they can be formed in a different structures. One is the core shell. When you use when you use two type of materials together to form a biometallic, they can be core shell, they can be heterostructure, and they can be intermetallics. The core shell structure formed when the material core, the first material which the first your precursor get reduced and becomes the core, and when the second materials reduce it, cover the surface of the previously reduced metal nanoparticles and form the core shell structures. Now this is another example of biometallics, but with a different structure, where the both the materials can reduce together, but they tend to attach with each other at a specific facets when such type of material formed. And these type of where one get diffused into the other, and this structure can be formed, which is called intermetallics. Now if you go for the XRD, you can find two peaks here. One is related to the core, one is related to the shell, and here also you can find the two different type of XRD. One is related to the first one, the second one is related to the second one. But in intermetallics, your XRD peaks cannot be found like related to your precursors. There can be new peaks. So this will tell this is intermetallic or not. You can identify like that. On the basis of such type of processes, there was one paper in the environment science and technology. They synthesized the biometallic. You will find a lot of papers, but this catches the eye because of their multifunctional capacity, and they remove the phosphorus and show the antimicrobial activity of the material. What they did, they took the commercially synthesized nano zero valent iron, they dip that into the AgNO3 solution. As the nano zero valent iron is very reactive, they, they tend to get oxidized or the passivate. They give the electrons to the plus ions and then get reduced into the Ag, when the Ag plus ion get reduced into Ag0. So this is how they form the biome, which is a very easy technique. And the stability of this material was very high because of the passivation was provided by this noble metal, which is not very reactive to the environment of the water. So they were able to get this results of almost 95% of the phosphorus, and like many species, they have seen shown the many uh, they have shown the antibacterial activity against the many species. This one is another example where the nanotechnology enabled these people to synthesize such a materials where they can easily get the three type of application at one go. What they did, they synthesized the iron based material and capsule and coated by the silicon rod coated by the iron like magnetite nanoparticles. So because of the presence of the particles, they get the magnetism. So that is very easy now. They can regenerate it by applying the external magnetic field. They remove the oil from the wastewater they took. They remove the dyes because of the adsorption, and they remove the heavy metal also because of the adsorption. So this is a very good example for a real water sample where you find, because in a lab you always find, you will always work with one pollutant or even in the very clean water, like and but in real world you will find an environmental sample where will be a lot of pollutants together. So this is filling a gap between the lab and the field. And coming to the disinfection processes, disinfection agents, this was done by my supervisor. He synthesized the uh, uh, good antibacterial, very good antibacterial agents by application of the CHX chlorohexidine and the silver precursors. So what he did, he oxidized the silver into the higher state. As the Ag3 plus state is very unstable in environment, so we have to encapsulate it with something so that this state can be maintained. And this state has the highest antibacterial activity amongst the other oxidation state of silvers. So what he did, he oxidized in the acidic environment, and then he encapsulated with a uh, biogonide agent, and then neutralize the neutralize the reaction by putting the bicarbonates, and then do it in a reverse and did it in a reverse microemulsions where the crystal growth can be formed, and he finds the very small nanoparticles. And he also varied the molar ratio of the silver AgNO3 and chlorohexidine, but he didn't find any change in the size of the silver nanoparticles. And when he went for the testing of the antibacterial efficacy against the AgNO3 and the silver sulfidazine and the other chlorohexidine compounds, his material was found to be the best among them, and he was able to publish it in the JACS, which is a very reputed journal. I guess this all ends. Uh, how I'm gonna summarize it, that by that quote by the speaker, that the nanoparticle doesn't have any application, and the application currently right now is nano, but they are gaining momentum globally, and because of their high surface area and the photosensitivity and the other antimicrobial activity, they can be employed for the treatment methods, as the effluent industry contains various pollutants, so we cannot rely on the monofunctional activity. So we have to think in a different way where we combine the application together, and we can achieve the multifunctionality, and that could be the best candidate for water treatment in the future. So challenges in the industries, like we are very fed up with the failing of the membranes. So in a tertiary treatment level, where they separating the various salts from the water after the secondary treatments, their membranes are getting filled and requires a huge energy consumption because of the pressures. Even after intercalating tear in these membranes, the detrimental effects of the UV, when you apply the UV for the effect for getting the effects of the TiO2 for the degradation of organic compounds, the structures of their polymerized membranes also degraded. So this is another challenge for nanotechnology. Also, these nanoparticles lose their inherent capacity when when they're in aqueous solutions. When they are in aqueous solution, they lose their capacity, and uh, for that we need to encapsulate them in a host or matrices so that they are not they don't become the any like, because the residual nanomaterial is also have to be managed. So when you apply it for the water, their management also should be go on the other side. The operational cost is very high, and the better understanding of mitigating them should be uh, understandable, and then only we can apply. Now we can say that even after a lot of properties, they can revolutionize the wastewater treatment. Yeah, thank you. That's all, Anupama.
Thank you, Deepak. Very informative talk. So now the session is open for questions. We have some box. So shall I say it for you, or you will go through them?
Okay, I'm trying. Can you also like jump to question?
Okay. I'll jump to the first question. So the first question was from from Prem Lata. wanted to know how freestanding graphene is functionalized with polydopamine, like you, I think, mentioned in fourth or fifth slide, I guess.
Oh,
Yeah.
okay, ma'am, they just they use the graphene oxide solution, and they are just applying this for a on a shaking position for 6 hours at 60 degrees Celsius, and after this time they're able to get this type of structures. So this is all I have got, because yeah, that's all I got from it.
Okay.
I have read the they use the graphene oxide solution and they put it into DS dopamine solution, which is self polymerized, and after a certain time, like 6 hours and 60 degrees Celsius, incubate for the 60 degrees Celsius. They are
You hope it's clear. Moving to our next question from Girish Kumar. Relationship between conductivity of semiconductor photocatalysts and their photocatalysis.
conductivity.
Yeah,
Conductivity of
semiconductor photocatalyst
and
and
relationship
their
between conductivity.
photocatalysis.
Okay.
Yeah.
Mm, Conductivity of semiconductors and the photocatalysis. So I guess the band gap which is there for any materials, it defines whether it can produce the electron in the holes for the photocatalysis. So if the material is conducting, you won't find any difference in differentiate. You won't able to generate the holes and the electron at the same time. That will be conducting, but in semiconductors, you have electrons and the holes together at the same times, which is able to generate the hydroxyl radicals because of the water molecule present in the aqueous environment.
Okay.
I
So
guess.
thank you.
Ma'am, I have one question, ma'am.
Yes, yes, you can go ahead.
So some of the researches are reports the scavenger study in photocatalytic reaction,
Yes,
which is used to
yes,
drop the.
yes, yes, yes.
But I don't know what happened inside the system, sir. Please explain it.
Even I don't have that much experience, but what they're doing, they're using a different scavengers like DMSO. I have read about it. They are using the DMSO. If they are able to catch that hydroxyl radicals produced in the environment, and the activity is reduced. Uh, I don't know. They're using the different scavengers to denote it, whether your material is able to produce the hydroxyl radical or the superoxide ions. I'm not very
Hello.
clear with it.
Now,
Clear
Okay.
with it.
Hello.
commercial lamp or sunlight, which one is for photocatalytic reaction?
Yes, Vasant, you can ask.
Commercial light sources or sunlight, which one is best for photocatalytic reaction?
Commercial light or sunlight, that depends on your material, I guess. When your material is able to perform in UV region, so you don't have to go for the visible light source. When your material is able to perform in the UV region, you have to go. And when your material is like silver and PU, go for the sun because it performs in the visible and the UV light together. I have read about it. I guess this is the answer for it. Obviously, sunlight
Yes.
is a free energy. You should always go for, but that lights always get deviated. Sometimes you get other type of flux. Sometimes you get a different type of flux. But there will be variability in the production of the hydroxyl radical.
Okay, sir.
Okay, so I hope it's clear, Vasant. So now going to our next question from Dr. Neha Dhiman. So she wanted to know, after adsorption process on industrial scale, whether the sludge of pollutants loaded adsorbent is discharged or recycled.
No, it is recycled. You can recycle with the acid, sometimes the acid treatment, and
Okay.
sometimes with the If you are using the nanomaterials, then you have to go for ultracentrifugations.
Yeah.
This is the 2-3 ways. If your material is high enough to go for the magnetism separation, then you go for the external magnetic field.
Okay. So next is from someone, maybe Mayank sir. Yeah. Can you highlight your work in this field briefly? Like your work in this field.
Haven't published any paper yet, but yes, we have successfully synthesized a biometallic material with the green methods, not using any plant bacterial uh, solution, but we are able to use the sunlight and able to synthesize some material, some biometallic species, iron and silvers. And after synthesizing it, we were able to show the removal of arsenic and the bacterial species together. So it was a material driven by the photo-driven mechanism. So we synthesis of material was very rapid that we could synthesize this material within 10 minutes. So we will be able to publish it. We already finished with the manuscript. The other work we are doing with the removal of different pollutants at the same time. So when there are different type of pollutants in the water, like this one is the anionic, one is the cationic, the material always show their capacity to remove the one type of pollutant. If you remove the one type of pollutants, you are not able to remove the second type of pollutants. You go for the second process for it. So we have uh, synthesized one material which is able to remove both the pollutants at the same time. I have shown you the papers which are already highlighted the microanalysis. That was my concern. The real water sample always have different type of pollutants. When you go for the lab experiments, you always do it in the distilled water, and you will find one type of pollutants because it is made by you. But in an environmental sample, you find a different type of pollutants. So you should the multifunctionality of the materials, and where bimetallic and trimetallic can play a big role. This is the work we are doing right now in our lab.
So that's really great, Deepak. So now going to the next question. Yeah, from Dr. Neha again. She wanted to know if recycling is the process. So which process they use for recycling? I think the earlier question ma'am asked, like regarding how can like after adsorption process on industrial scale, whether sludge of pollutants loaded adsorbent is discharged or recycled.
Yeah.
So you said it's recycling process, I guess. Yeah. So she
in
wants to know
industry, they might not be doing it, but at large industry, I guess we have visited one industry, IOCL. They were recharging it. They were washing them, giving acid treatment, and they were filling it again.
Okay. So acid treatment is the process, right?
Yeah.
Yeah. Okay. So there is one more question from Girish sir. He want to know why does band gap energy of quantum dots vary with its size?
No, I have no experience in quantum dots. Nukuma, can you please explain this? If you
Yeah, actually, okay, we'll take it later. We can take it later. So next, going to the next question. So some nanometal oxides are toxic in nature, like copper oxide and CDS, but still they are used. So yeah, copper oxide and CDS.
Yeah, that is
So
the
she
reason.
wanted
That is
to know why they are
when
used.
we are lagging. So nanomaterial itself become a big challenge for us to manage for a management. So that is why I was saying there is a gap between the real life lab life. Nanomaterials are able to remove a lot of pollutants, but when you comes for their management and for the real water samples, we have a huge gap where we have to look upon it. So CDS and the CuO, you are saying they are toxic in the nature. We have to uh, search out some matrices or some polymers where we can intercalate them and where their leachability of these material can be minimized. Their application will be same, but their leachability should be reduced. So this is the solution right now we can do, I guess. Others, I guess, I don't know if there are people are talking about it or not.
Okay. So yes, they are good visible light sensitizers also. Like
Yeah.
so, because of their good activity, like light sensitization, that is the reason that we need to use them because they are highly. So
Yeah, true.
we need to cope up with their toxicity. So next is from you want you to will it react with oxygen, water, rusting?
Yeah,
So
it
you
always get
discussed some iron
oxidized.
paper, I guess.
Yeah, it always get oxidized, and you will find a small layer of oxides. It, hydrox- oxides,
Yeah.
and sometimes you get the combination of both, Fe3 or Fe3O4.
Okay. So next, he has to say like one more question. What is the role of core material in nanoparticles, and how it's going to react with water?
The core is always present in the middle of the materials. It tends to oxidize and it produces electrons at the surface. It is giving an electron, so the electron can generate the ROS in the your aqueous environment where radical can be formed. This is the application of core, I guess.
Okay. Plus, it helps in like energy transfer mechanism. If you have any material like would have a higher band edge,
Yeah.
so channeling of electrons take place. So core has a role to play in the combination basically and
Yes.
like shell. So we need to choose materials in such a way such that electron channeling can take place, like its proper activity. So that could be one reason. So next, coming to the question from again Dr. Neha, she wanted to know why industries are mostly using TiO2 and ZNO for catalysis. Why they do not use any other
Ma'am,
catalyst
TiO2
large
I can
scale?
say because TiO2 is low toxic and very cheap. So you can go for TiO2. That is why other materials would be very expensive for it. And you can go for the like scale up application. People are using TiO2. Also, it has capacity when for the generation of uh, uh, and electrons when proper light is fall upon. This is the reason. Nano is also a non-toxic environment. Maybe that is a it, and also it has a very good photosensitivity to produce the electrons in a hole.
Yeah, they both are wide bandgap semiconductors, so that is one possible reason. Scale in industries.
How adsorption and photocatalysis.
Yeah, applied on large scale in industries.
Adsorption is being applied with by the help of activated carbon. Uh, you will find sand filtration and there will be a lot of layers in between the sands of activated carbon. So they are doing that together or sometime with the separately. So this is where the adsorption being used by the industries. And photocatalysis, they are just using the UV treatment. I haven't seen any industry by myself, but I don't know whether people are using it or not. In papers, there are a lot of reports, but I haven't seen any industry using it. Yeah, activated carbon is being used very efficiently.
Okay, so next is from Jinnat. She like wanted to know what is the most effective process for regeneration of nanomaterials after use in water treatment.
So one is the treatment by
Yes.
your maybe by the NOH and the HCl. The other is the centrifugation. These are the two treatments I have read in papers. There may be others also, but these are the two famous I have seen in papers.
Okay, so one more question from Girish sir. He want to know how to calculate the turnover frequency and amount of catalyst active sites.
That I don't know. I don't know. I am
Yeah. So sir, we'll
Anupama
get
and
back to these
Alika will
questions
help
in a
me.
minute. Yeah, actually, sir, if you're talking about like, I have been working on photoelectrodes, so we generally use for calculating these like turnover frequency and active surface sites. We generally use the CV, cyclic voltammetry. So by the Faraday region where the electrode behaves well, from that region we calculate the capacitance, and based on that we calculate the active surface area by using cyclic voltammetry. So that is one way of doing it. And likewise, when we calculate the active surface area, so by using that and plus the current, we can calculate the turnover frequency. So we do it like that way, by electrochemical, by electrochemical processes. So next, Aryan has a question. Sir, you mentioned about the magnetic removal method, in which Fe is added to silicon and then removed magnetically. Doesn't the added Fe make the water toxic?
No, no. You have. So you mentioned. Can I read it?
Yeah, he's
Fe is
asking
added
like
to
you have mentioned
silicon.
about magnetic removal.
Okay.
Yeah, magnetic removal method in a paper you have mentioned.
Yeah, yeah.
Yeah.
Iron is
He wanted to know
very
in
iron is not toxic to most of the environment. So I would say that that is not that much toxic, and that because of mag- properties inside. I don't.
okay. Your voice is getting like cracked. Some disturbance is there. Yes. Deepak? Yeah, Deepak, are you there?
Okay. Oh, sorry. Sorry. Okay. Yes, yes, I'm here.
Yeah.
Hello.
So something you would like to comment on magnetic removal method? So he wanted to know is like, does this iron make water toxic?
No, I answered it. I guess the voice was not clear. I was saying that iron is not considered to be much toxic for environment. So being the toxicity, I mean, talking about the toxicity, the iron is not very toxic to the environment. So you can go for such type of materials because they are considered to be very environmental friendly. That won't go for any toxicity portion.
Sir, I would like to add a little thing to the question.
Okay.
Yes,
I have read it somewhere that ferrous chloride and ferric sulfate are somewhat lethal to the human body. So, like in real life, how can you say that that iron will only react with silicon and that can be magnetically removed? What in case if that iron is reacted with that chlorine and sulfate ions present in the water? In case that consumption can be lethal, na?
The silicon, I haven't mentioned anything about the silicon. I guess I mentioned about the silver and the iron.
Iron,
Hello.
he
You
mentioned
will.
about the silver and the iron during the
Yeah,
magnetic
I
removal
mentioned about
method.
On
the
that
silver.
slide, there was somewhere present silicon. That
Yeah.
was my doubt. There was somewhere silicon present on that slide along with iron.
So you can
That might
get
be.
back to that slide. Deepak?
Yeah, yeah, I'm
Yeah.
sharing it.
Yeah, you can share your screen and go because clarification will clear things. Yeah.
Yeah.
Yeah, can you see it? This was the slide,
This
I
was
guess,
the
where
slide.
iron and silver is there.
No, sir, previous
Oh.
one, previous.
Previous one.
There was one more slide previously of iron and silicon.
Right. No, I have shown this as a iron source, iron water treatment candidate, and this, which is being encapsulated in the carbon matrices. There is no silicon I have mentioned anywhere. No, there is no silver. I haven't mentioned about it.
I think iron, there may be
Yes, sir,
some
yes, yes, sir. This
yeah,
was there,
there may
this
be
silica.
Silica.
Yes,
this
sir, yes.
No, that okay, okay. That is
In the middle image,
yeah,
this is mentioned, na, iron with silicon.
yeah.
no, no,
It's not.
that is iron oxide,
Yeah,
I guess.
SiO2. Yeah, it is
Okay,
iron
okay, okay.
oxide
Got it, got
added
it.
over this.
Yes, sir.
Yeah, silicon oxide. Yeah.
Okay, sir, okay, got it.
Yeah.
Okay. Anupama, please take up the next question.
Yeah, next we have from Jaspreet Singh. So, sir, want to know
Okay.
that. Yeah. So, he wanted to know, could you throw some light on RO purifiers, which is largely available in today's market? Is it really does it really purify the water?
Yeah, they have a very good efficiency. The nanofiltration and the ultrafiltration, that these are all being used, and the RO which is being used, they have a very good efficiency, but they always require some pre-treatment before them. Because without pre-treatment, your membrane get accumulated with a lot of TDS, because the industry always have a lot of TDS even after the secondary treatments. So you always have go for the pre-treatment, which is done by the other membranes or by the activated carbon.
Okay. So, hope it's clear. Next, we're going to Abhiram Anand's question. So, he wanted to know, can you tell me how do you account for toxicity of MOS? Like, I think it could be it would have been MOS too. So, isn't it carcinogenic because it belongs to chalcogenides family?
Alcogen family.
Yes, MOS too.
Yeah, they could be, but again, I was telling you about have to intercalate them in some matrices for to reduce their toxicity. MOS can be, yes, MOS2 can be toxic also, but when you use it in a very huge amount, and obviously anything which is more than the requirement will be toxic. So I guess we should always go for some matrices to intercalate them to stop their leachability. This is, I guess, this makes clear. This makes sense about it.
Yes.
Yeah. So next, again, like Aryan is asking, you have shown MOS to nanosheets for cationic removal. So,
Yeah.
can you clarify the technique used for anionic removal?
Yeah, you can go for the different layers which have the positive charge on it. Like I have mentioned, the LDH, layer double hydroxides, which have the very positive charge over it. And when you go for such anionic removal, you can always go for the such type of sheets which have the positive charge. When you apply that materials, you will be able to see the removal of the anionic species.
Okay. So, okay, so there's one more question. Yeah, from Girish sir. Sorry, I missed it. What is the relationship between COD, BOD, and TOC in water?
Yeah. This is not a part of my experiments, but still, COD is always greater than BOD, and if the ratio is more than 0.6, then you always have to go for the chemical treatment. You will find there is almost 150 mg per liter of BOD, and the COD can be goes to very high, like 350 to, if you go for a
Yeah.
textile, that will be hundreds and
More
thousands.
the pollution,
And the
more will
TOC
be the
is,
same.
yeah, and the TOC is the total amount of the carbonic species which is present in the wastewater.
Okay. So, how does morphology of materials affect catalysis? By Sumant. This question is from Sumant. How does morphology of materials affect photocatalysis?
Yeah, when you go to the nano scale level, their band gap changes. So that can, like if you talk about the bulk MS2, their band gap is somewhere around 2, I guess. And when you go for the nanoscale level, the band gap changes to 1.88. So that makes it candidate which can produce that can be act as a photocatalyst when you use the visible resin. So morphology have a very good impact on the band gap.
Yeah, more light harvesting with a
Yes.
small size. So
Yes,
it
yes.
affects. Next from Webber, while purification of water, do these filtration methods affect necessary minerals in water?
Yes, they are fixed, but I guess um, that even after your filtration, you will find a lot of TDS in your samples and the minerals in your samples. So the industries are using these filtration techniques to reduce the TDS. But after that, you also have, maybe you have the chlorination, then you have some RO system to reduce that. So every membrane has effect on the mineral composition of the water also.
Okay. So thanks. Next, one more question. In case of iron, like nano iron, we can't use acid for regeneration. So what for that case, what should be effective procedure?
Iron, that what I was saying. The iron being as a magnetic responsive. You can go for magnetically. You can apply the external magnetic field, or you can go for the ultracentrifugation, where you can separate your material from the water aqueous solution or the some where you are doing your reactions.
Okay. So which technique is used to monitor degradation process from Vasant?
Which technique is used to monitor the degradation process? That depends on your pollutants, how you are monitoring them. If you are using bacteria, you can go for plating method. If you are using the organic dyes, you can go for IR techniques, or the UV techniques, or the fluorescence techniques.
Yeah.
That depends
If you're
on
using
the
any
pollutant.
photocatalyst, so you can go for UV spectroscopy and monitor
Yeah.
changes of degradation. Yeah. So Aryan, again, sir, for how much long a particular type of nanomaterial can be used if we talk about air or water pollution? For how long can we use a particular material and are they cost effective?
No, that depends your recyclability. People always go for the recyclable test also. Once they perform one experiment, they recharge it and they try to check whether the efficiency is still there or not. So they sometimes they go for 5 cycles, sometimes they go for 10 cycles, or sometimes one cycles can totally degrade the active sites or the structure of your materials, so you won't be able to use it again. So there are different studies through you can define or validate materials, whether you can use it or you can recycle it again for next generation, next experiment.
Okay. So next is from Abhishek Seni, sir. So he wanted to know like what is the impact of nanomaterials or nanoparticles on different aquatic animals, like organisms?
Yeah, we people are still reporting a lot of papers about it, because I was already telling the nanomaterial itself becomes a toxic for human being as well as for the environment. If you engulf the silver or you come in contact with the silver, a lot of you can be you can be got the disease ergeria, and these nanomaterials can also run into your bodies and they can go into your CNS or something else. They can induce a lot of toxicity inside the human body and the other organism also. There are reports.
Yeah, this is under investigation yet. Like how
Still,
can
yes.
we get rid of their toxicity? So it's better to use eco-friendly nanomaterials. We can synthesize like eco-friendly nanomaterial like carbon quantum dots.
Yes,
There
yes.
can be eco-friendly. We can switch to eco-friendly materials and get rid of it, or do some functionalization onto some materials
Yes.
so that it does not affect like life. So next is from Vasant Kumar. How band gap and particle size will affect the photoactivity or
I guess
photocatalytic
we have
activity?
discussed it. I guess we have already discussed about the morphological impact on the band gap, right? Photocatalytic activity.
Yeah, so larger band gap will actually result in the light absorption in the UV region, and
Yeah,
smaller the band
it
gap,
is
so it will get extended towards visible and IR.
visible.
So
Yes,
smaller band gap like MOS2 has 1.23, so it is a good visible light sensitizer.
yes,
But if we talk about TiO2, it is 3 electron volt. So it like harvests energy good in UV region. So that way band gaps play a role. So next from Aryan, so this will be the last question, I guess. So are these nanomaterials cost effective? On what factors does it its cost affect? Yeah.
Yeah, that's what I was asking to that scientist in that workshop, and he said the application of nanomaterial in wastewater treatment is still nano. So that's how we can see that right now the condition of nanotechnology in the water treatments, and just because they are a cost and their application and their toxicity, we are not able to use them in the water treatment. Yeah, they are very
Yeah.
costly. Operation and maintenance cost is very high when you're yeah, when you're using nanomaterials in water treatment.
Yeah, true. Plus, nano is emerging still.
Yeah.
So then we are investigating, like people are investigating several things, several technologies to make them cost effective and for the mass production. So it is still
Hmm.
emerging, we can say.
Yeah,
But they have very
one
like
more
good.
point I want to add. If you go for
Yeah.
monitoring of any water treatment plants, you will find right currently you will find a lot of PPCPs, you know, which are the emerging concern, and right now they are inducing a lot of disease and lot of emerging what we call it, like when the bacterial strain get accumulated when जब वो क्या हो जाता है when it get adapted to some medicines like diclofenac and all, then you need a new medicine. So where the nanomaterials will play a big role. So nanoparticles is very hard to adapt with, because you can adapt against the antibiotic, but against the nanomaterials, the bacteria cannot adapt. This is where the nanomaterials will play a big role. But right now, yeah, we are still under construction of it. Let's see what will happen in this field.
Yeah, hopefully. So
Anupama
there was a
madam,
question
may
from
I ask
Ganesh, I
from
guess.
voice question?
Yes, sir.
Madam, I am Dr. Veeresh S.J. I studied environmental science, MSc and PhD also. Hence, I am
Yes.
requesting, you are doing very well work, but how now this biotechnology becomes evil now today, sir. Yes, sir. When we are going to research nanomaterials, that could be in future, it will may become a evil. Hence, we have to search for a sustainable that is not affect to environment in future also. On the type eco-friendly and maybe this nano technology maybe effect maybe in future every material we are farming that is effective formation when we prepare any substance by using nanomaterial that may cost in future very much. Yes, we could take now only the concern about the sustainability also meanwhile.
Yes, sir, you're right. That is why people are
Yes, sir.
jumping to the biogenic synthesis. But
Yeah.
still, that is not possible to control the shape and size or the desired property during the biosynthesis of such type of nanomaterials. That is where people are still using the chemical based techniques for synthesis. This is the space we need to fill with the help
when
of
we when we
any
are
other agent. Yeah.
when we are approve the any scientific investigation to adaptation and then are conventional purposes, we have to have a certain legislation which are the materials to be permitted or not permitted, then only we have to control the such effect in future.
Yes, sir, you're right, sir. I agree.
Okay, thank you, madam. Thank you.
Thank you so much, sir, for the discussion. So we are looking and heading towards sustainability of nanomaterials, and in time we look forward that we'll be able to tailor materials in a way that they are like they could be sustainable as well as cost effective. So material scientists and all nanotechnologists are working in this area. So hopefully in near future we'll get some very sustainable materials that we can use in various applications. So thank you all. So there was a question from Girish sir, I think, regarding quantum dots, like the relation between band gap energy and the size, I guess. So, Sir Rishabh has answered in the chat box window. Like variation of band gap energy of quantum dot is due to size, and that is mainly due to quantum confinement effect. So this could be one reason for the question you have asked. So thank you all for joining us. So before we end today's session, let's have a group picture with our speaker. So now you all can turn on your camera and we can have a group picture to make it memorable. Yeah, so I'm waiting for people to join in. Yeah.
Thank you for giving this opportunity. Okay.
So thank you. So see you all tomorrow.